Imagine trying to keep a whisper secret in a crowded, noisy room. It is a delicate message, easily lost or distorted by even the slightest disturbance. Now, imagine trying to protect information even more fragile than a whisper, information that changes just by looking at it. This is the challenge we face with quantum bits. So, how do we shield these incredibly delicate qubits from the constant barrage of errors? To protect qubits, we're relying on a specialized family of techniques called quantum error correction codes. There isn't just one single code, but rather various sophisticated methods, with some of the most prominent being stabilizer codes, which include the well-known surface codes and color codes, as well as topological codes. These are not simple backups. They are ingenious systems designed to preserve the integrity of quantum information. The reason we need these unique quantum codes stems from the fundamental differences between classical and quantum information. In the classical world, you can easily copy data to protect it, but the quantum no-cloning theorem forbids perfect copying of an unknown quantum state. This means we cannot simply make backup qubits. Furthermore, quantum errors are more complex. Instead of just a 0 flipping to a 1, qubits can suffer from bit flip errors, phase flip errors, or a combination of both. A bit flip changes a 0 to a 1 or vice versa, similar to classical errors. However, a phase flip error alters the relative phase of a quantum superposition, which has no classical counterpart and can be equally damaging. Quantum error correction addresses these challenges by encoding one logical qubit of information across multiple physical qubits in an entangled state. This redundancy allows us to detect and correct errors indirectly, without directly measuring or disturbing the fragile quantum state itself. The code essentially spreads the information so thinly across many qubits that no single error can destroy it entirely. The core idea behind these codes is to measure something called an error syndrome. This syndrome measurement provides information about whether an error has occurred and, crucially, what kind of error it was and where it happened, all without revealing the actual quantum data. For instance, in a stabilizer code, a set of operators, called stabilizers, are applied to the encoded state. If the state is error-free, these operators return a specific value. If an error has occurred, they return a different value, indicating the presence and nature of the error. Based on this syndrome, specific recovery operations can then be applied to restore the logical qubit to its correct state. This process is repeated continuously to maintain the quantum information's integrity. A critical characteristic of any quantum error correction code is its code distance. Often denoted by the letter D, this code distance essentially tells us how many errors a code can correct. Specifically, a code of distance D can correct up to D-1 divided by 2 errors. For example, a code with a distance of 5 can correct up to 2 errors. Higher code distances requiring more physical qubits to encode one logical qubit but offer greater protection. Early conceptual codes, such as the 9-qubit shear code or the 7-qubit Steen code, laid the groundwork for these more advanced techniques by demonstrating the possibility of correcting both bit flip and phase flip errors simultaneously. These foundational examples proved that quantum error correction was theoretically valuable and paved the way for practical implementations. Ultimately, quantum error correction codes are the unsung heroes vital for the future of quantum computing. By creating robust quantum states that can withstand the unavoidable noise and errors inherent in quantum systems, they transform inherently fragile qubits into reliable units of information. This enables the construction of fault-tolerant quantum computers, which are essential for tackling complex problems that remains intractable for even the most powerful classical supercomputers. They are the bridge from noisy, experimental quantum devices to powerful, scalable quantum technologies.
If quantum tech fascinates you, like, subscribe, and keep exploring with us.